Yes, hi everyone. So I'll move to a little bit out of the main focus of this conference, which is Tibet and the Himalayas. So I will take you a little bit to the east, to Taiwan, and I would like to talk about aseismic deformation, in particular in the setting of a fold and thrust belt. So this work includes quite a few collaborators. So yeah, for those who don't know me, I graduate from this lab maybe 16 years ago about. So I have a classical neotectonic background with also some geodesy. And in this work, we continue to combine Holocene deformation along with geodetic observations. And for this work, I need to acknowledge, in particular, Jing Ho-en, who did a lot for the inversion and data collection for this work. Okay, so so when we talk about aseismic deformation, actually most of the creeping fault segments on continental Earth are strike slip fault segments. And we have one reverse exception, which is Sheshang Fault, still in Taiwan. And Marion and Jean-Philippe worked on that fault a few years ago. And however, if you dig into the literature and look into aseismic deformation in the context of fold and thrust belts, you see quite a few cases of aseismic triggered slip or after slip that was observed mainly from INSAR observations in places where salt and shales are present in the deep structures. So I list here a few of these events. One of them actually occurred in southwest Taiwan. And among some of these events, there has been observed or suspected aseismic deformation prior to those earthquakes, but this is just not investigated that well. Probably it's difficult to measure that without a ground-based network. So in the study I'm going to show you today, so it's in Taiwan, the field is easily accessible. You can put a lot of GPS stations with quite good spacing, and you complement that with INSAR. And if you are lucky to have a beautiful river crossing over the place with beautiful terraces, then you can have some nice results like you will hopefully enjoy later. Okay, so Taiwan is located here, so it's just kind of at the eastern boundary of this Eurasian continent that we looked in great depth in the past day and a half. So Taiwan is at the junction between two subduction zones, and we have a collision system between a volcanic arc and the Eurasian passive margin. So the collision is quite fast, 8 to 9 centimeters per year. It's also very recent, only since late Miocene. And so just to give you a rough idea about the structures here. So in the central Taiwan, where the Tiji earthquake occurred, we have a kind of continent to volcanic arc collision system. But as you go towards the south, you see here that you have here the edge of the continent. So when you go towards the south, this continental crust becomes much thinner, stretched, and the basin becomes deeper. So the foreland basin sediments also become more clay. And we will see that this probably have some this is probably an important factor in the deformation we are observing. Okay, so so talking more about active deformation, this is a strain rate map across the island. And so most of the deformation is accommodated in the east and in the west. And you see that in the southwest, the strain rates are very large. And also the seismicity in this region is extremely low. Okay, so I zoom in this little corner here, and this is a geological map. So when we look at this map from the west to the east, so in the west we have a coastal plain with Holocene sediments and buried anticlines. And when you go towards the west, you have older and older sediments, so mainly Pliocene, Pleistocene, and at some point you meet these large thrust faults that bring Miocene sediments on top of Pleistocene sediments. Okay, so these are sections that I will show later on, and here is a river system that goes across these structures. Okay, let's look at active deformation. So these are horizontal deformations from GNSS, and the scale is up there. So basically, from the eastern part of this map to the western part, we have about 3 centimeters per year of shortening over a place that's maybe about 20 to 30 kilometers wide. Okay, so we do have INSAR observations in this region. So this is a data set from Lu et al. 2024. It's a PS INSAR processing of Sentinel-1 images. Okay, this is the scale bar here. So you see that across this area, we have kind of orange value, and going east, this is increasing to red, so about 20 millimeters per year in the line of sight. And suddenly it's dropping to close to 0 in this region. And as you may see, the gradient across here is quite strong, which suggests ongoing aseismic deformation. Okay, so we are going to look more into these structures. In this region, we have a major thrust fault. We have an anticline here and a back thrust here, and the gradient seems to align with the back thrust. So let's look at what Holocene deformation shows. Okay, sorry, I go a bit too fast. So in this talk, we will have kind of 3 approaches. So first, we will look at Holocene deformation from river terraces. Of course, in the field, we combine that with intense field survey. Then, in parallel, we will look at decadal interseismic deformation rates. So actually, there is a data set, INSAR data set with ALOS1 data, Sentinel-1 data. All of this is published. It's not done by me, GNSS and leveling. And in this study, we combine those to make to produce a 3D velocity field, and to invert this. In the inversion process, we allow for velocity discontinuities along the inferred creeping fault. Okay, and then to wrap up everything in the fold-on thrust belt, we always need to look at how structures may look like at depth. So we will look into cross-sections to determine the geometry of the faults responsible for the deformation. Okay, so to quantify Holocene uplift rate from river terraces, so we usually measure the terrace height relative to the modern river. Okay, so that's the red part here. And along most rivers, probably those terraces that we observe will be buried somewhere in the footwall. So to get the true vertical deformation, we need to combine these heights in red with the burial depth in the footwall in blue here. And this is assessed by boreholes. Okay, so to get these rates, we did a lot of field work to observe terrace deposits and get observations of the contact between bedrock and terrace deposits. At some sites, we actually observed fluvial deposits interfingered with coastal deposits. So in addition to the method I just showed, we can compare our uplift rate with uplift rates that we determine using a sea level curve. So we have two methods kind of independent at this site that we can use to compare. Okay, so here we have a beautiful outcrop of this backthrust called the Koshari Fault. So we have Pliocene rocks against Pleistocene rocks, and you see that this fault propagates on top, brings all the layers even on top of terrace deposits. We have a few ages from charcoals there. Well, they have some variability at this site, but yeah, eventually it won't matter too much for the rest. At this outcrop, we can also observe kinematic indicators that unambiguously mention that this is a river fault. Okay, so after we combine all these field data, we have a kind of final terrace map, and I will zoom into this region here. Okay, so terraces are mapped here from youngest with the yellowish color to oldest with darker red color. And we observe terraces that are all within the Holocene. So the oldest is about 9,000 years old, and the youngest that we dated about 2,000 years old. From the morphology, I mean, you can see clearly this river is a meandering river. And from the terrace pattern, you can recognize, so yeah, here between in the inner part of the meanders, the terraces being older to younger, and some risers have the same curvature as what would be from a sinuous river. Okay, so the oldest terraces are mainly located in this area, so close to the anticline axis. But we managed to have terraces of various ages all across the study area. So deformation will be easier to see using a profile. So here we have the distance from west to east, and here the elevation. The modern river in blue and the terraces using the same color code. So maybe we can focus on the orange. Sorry, this is pink. Yeah. So yeah, so on that pink terrace level, so we see that, okay, we have maybe 40 meters above the river here. And when we go towards east, now this same terrace level dated at both places, 3.5 to 4,000 years. But at this location, the terrace is more like 70 meters above the river. And then we go further east, we cross the anticline, the thrust, the backthrust, and we reach to here, and this same terrace, which is also dated, here, is maybe 30 meters above the river. Okay, so we could do the same observations with 8 to 9K terraces, low elevations here, much larger here, and much smaller again here. Okay, so from that profile, we clearly see that we have some active uplift in this region, and the uplift is decreasing towards the west, kind of gradually. And across across these structures, we have a major decrease in uplift. So unfortunately, we have this orange terrace here doesn't look offset by the fault, but it's only 2,000 years old. We were not able to date this one. So from the Holocene deformation alone, still it looks like this thrust would not be active, and potentially most of the action would occur along the backthrust. So now let's look at uplift rates from these terraces. So now we have still the same distance axis and Holocene uplift rate relative to the coastal plain. Okay, so all these colored dots correspond to those terraces, and we can recognize the same kind of pattern with increasing uplift towards the east. We reach some kind of plateau here, and uplift rates drop across the backthrust. Okay, so I mentioned before we have a site where we can calculate Holocene uplift, like based on the kind of river evolution, but also based on a sea level curve. So to see this result, you need to compare these dark red dots with the blue dots. So blue dots are inferred from sea level curve, and we get actually very consistent results. Okay, so here it is for the Holocene. How about present deformation? Okay, this graph looks scary, so let's look at it little by little. So you will, you recognize in yellow the Holocene uplift rate, and here I add in green. So in green is so the kind of dots here are the vertical component from PS in SAR. Okay, so and the thick green line is the result of the 3D velocity field. Okay, so you can see that these green observations or model data versus the Holocene profile in yellow, the pattern looks quite similar. Okay, so we have a little gap here, a few millimeters per year, but overall the pattern is the same. And from the inverted velocity field, we see here that the data really support discontinuity along this backthrust. So the gradient is extremely strong, that supports aseismic slip, and the similarity between the cumulative deformation in yellow and ongoing deformation also suggests aseismic deformation. Okay, here in blue, I also included the horizontal component. So the arrows are GPS, GNSS data. So from GNSS data, it would be difficult to argue if the deformation is, if shortening is kind of gradually decreasing, or if we have any step. So that's where the INSAR data become very useful, as well as the inversion, because we really see here a gradient in horizontal deformation that matches with the backthrust. Okay, all right, so yeah, so we have aseismic deformation going on here. We have aseismic faulting as well as folding, right? These terraces are folded. So in the next question is, okay, what kind of structure is producing that? Because within short distance, we have all these structures. So what is their relation? So to investigate this question, we go into building some cross-section. So here is, the observations we have. So we draw a section, about 40 kilometers long. And here I kind of summarize the data, the observations we have to constrain this cross-section. So we have, of course, surface geology, a few boreholes, Here we have a seismic line, which is in two-way travel time, not depth converted. And here is the cross-section that we came up with. And I think we will mainly focus in this area. So so here we have this buried anticline, then this tight anticline here, very tight, very narrow. So it cannot root very deep because it's so narrow. And then we have this thrust that brings the Miocene to the surface, and this back thrust here very close. So to explain this deformation, I propose that because most of the active deformation occurs on the back thrust and anticline, so I actually propose that this back thrust would root to some depth at some detachment and actually cross-cut this former geological faults. So that could explain why this thrust fault would be now inactive. Sorry, there is also seismicity on that map. And you can see that most of the earthquakes are deeper than 6 kilometers or so. There is nothing happening in the shallow, the upper few kilometers. Okay, so now that we have a kind of structural model, we can try to use that to determine fault slip rates. So when we look at the surface geology here and the proposed model, we see that the dips as well as the uplift are increasing towards the west. So a simple model that we can think of is just a fold band folding model. And to use this model to calculate to calculate slip rate from uplift, it's relatively simple because uplift would be proportional to slip times the sine of the ram dip. So this model is simple, easy to use. However, one of the assumptions is that bed length and layer thickness remain constant during deformation. Okay? All right, so if we accept these assumptions and just, to try to determine a slip rate. So we get actually the area in pinkish orange. Okay, so yellow is the Holocene uplift rate, and the orange is expected uplift with best fit slip rate of 23 millimeter per year along this deep detachment. Okay, so of course this doesn't fit perfectly. Okay, I think we can discuss those limitations. So another thing that we wanted to look at is what are the factors that may favor a seismic slip in this area. And there is an old borehole from the, 70s or 80s drilled within this anticline axis. And along these boreholes, we have lithology, and we also have resistivity. And we see that the strata at depth are quite muddy. So the more pink here means muddier fishes. And from the resistivity profile, we can see that in this area, resistivity becomes lower, which is usually interpreted by a larger amount of fluids. Okay, so if I wrap up with conclusions here, so we observed aseismic deformation. We managed to propose some kinematic geometry, and we also find that clay-rich lithologies and the presence of fluids may favor creep which is not a scoop for anyone here, but at least we have nice observations here to solidify this common observation. Okay, I will stop here. Thank you for your attention.